Hello everybody, today we're going to be talking about Unit 2 of AP Chem, and we're going to go over every subunit as best I can, and let's get started. So, the Unit 2 as a whole for AP Chem is primarily composed of molecular and ionic compounds, and more specifically their structure and their properties. So let's get started. In Unit 2.1, we're going to be talking about molecular and ionic compounds and their properties. Alright, so there's three main categories when we're talking about these compounds. There's covalent, ionic, and metallic bonds. And covalent bonds can either be polar or nonpolar. And ionic bonds will always be ionic, and same for metallic. But ionic bonds are charged particles attracted to each other. And nonpolar are when two electrons are shared equally between two atoms. And polar is when they're shared unequally. And for metallic, you can have positive cores. So when we're talking about ionic bonds, we're going to have to be focusing on a couple things. So first off, there's going to be positive ions and negative ions. The positive ions are called cations, and the negative ions are called anions. Their properties are brittle, stable, and they're easily soluble, particularly in water. So here I'm drawing a diagram of ionic bonds. As you can see, the bigger green circles are the negative anions, and the smaller black circles are the cations, and they're in a pattern alternating each other, and this alternating maximizes their repulsions and attractions to keep them very stable, so they're not moving. So obviously this is a 2D version, as you can see, but it's in real life it's an actual 3D version, and I can't draw that, but we call that a lattice structure, and that is basically the same thing as my drawing, but it's in a 3D pattern. So when we're talking about covalent bonds, there's a couple things to know. So covalent bonds ultimately share electrons, and they want to have a full outer shell, following the octet rule, which is 8. And we're going to see a battle between polar and nonpolar, and we'll get to that in a bit. But here, let me draw CH4. So there's a C and 4 H's. CH4 is methane. And all H's have one electron, as you can see by my drawing. Sorry, those red dots are the carbon electrons, and those blue dots are the hydrogen electrons. So hydrogen sharing its electrons with carbon 4 times. So this would be a covalent bond, particularly nonpolar. So let's dive into nonpolar. So there's sort of a battle between nonpolar and polar bonds. Nonpolar versus polar. So nonpolar electrons spend an equal amount of time on both sides or with each atom. And obviously that's the opposite with polar bonds, which they spend unequal time. So let me show you a couple drawings. So as you can see, this is Cl2, or chlorine gas, and Cl has 7 electrons, so that's why I didn't put 8 dots, and then on both sides. Now you see in the middle, there's 1 blue and 1 red. That's because they're sharing, but they're sharing equally because the shape is a complete equal circle, and they're sharing it, right? But now you see here, it's not an equal shape, where there's HCl, which Cl has 7 and H has 1. So H is going to give up its electron to Cl in order to reach an octet. And however, they are sharing, but the shape means that they're polar because one side has a positive charge and one side has a negative charge. And those signs are deltas, and they reference the charge, and also that line, the arrow points to the direction of the negative charge. So how to tell? So basically, you have an electronegativity chart if you look it up online, and there's values that can help you. So if the number is greater than 1.7 it's ionic. If it's greater than 0.3, it's polar covalent. And if it's less than 0.3, it's nonpolar covalent. So that's a little trick to help you remember it. Okay, so for metallic bonds, it's a little different. So we have large positive cores. These are positive protons, or you could say cations, and there's a lot of them. However, it's not as formal as the lattice structure of ionic bonds. They're all over the place. They go everywhere, and they move between them of their own free will. So we call this the sea of electrons, and those orange circles are the electrons, and they just move around the positives as they want. Yeah, so as you can see, the positive cores are the metal ions, and then when we see these little dots in between these electrons, these are the metallic bonds. And because they're moving, alright, so moving on. Now we're on to Unit 2.2. And that's basically intramolecular force and potential energy. So we're going to first talk about bond energy. What is bond energy? Bond energy? So bond energy is energy stored in a chemical bond. Simple enough. Anyways, here's a little graph to help explain bond energy. So this red line simply symbolizes the balance between the attractive and repulsive forces. Now we're going to draw three lines: green, red, and blue. So the blue chart represents single bonds because they have the lowest bond energy. And the red is obviously going to be a double bond, which represents a larger bond energy, and triple bonds, which have the most bond energy, as you could imagine. Now we're going to talk about lattice energy. As we talked about before, lattice structures are the representation of ionic structures in a 3D model. So lattice energy is how tightly an ionic crystal is held together. So if it's negative, that means a bond is formed, and if it's positive, a bond is broken. So now let's go over some questions, and if you want to pause the video after I've written down all three questions, you can check them with me afterwards. So the question asks, which has the highest lattice energy? So there's three questions: Mg, O, and NaF. So we're going to compare those two. We're going to compare Ca and F2 and ACl3. So our first step is to write the charges. O has a -2 charge, Mg has a +2 charge, Na has a +1, and F has a -1, right? So that means overall MgO has a -4 charge. So we're going to do that for all of them, right? Ca has a +2, F -1, and we're going to do that for all of them. So very simple. So our focus is which will have a higher negative sum. So as we see in MgO, there's a negative sum of 4, so obviously it's MgO. There's a -3 sum of ACl, so therefore it's ACl. But what happens when they're both the same negative charge? We're going to look at which of the two is smaller in size, because they both have the same charge, so we can't determine. So Na is smaller than Sr, and O is smaller than I. So therefore, a shorter distance means stronger lattice energy. So now we're going to talk about 2.3, structure of ionic solids. So ionic solids are ions that align themselves to maximize attraction and repulsions. And we can see that through the lattice structure. So lattice structures are held together by electrostatic force and attraction. And this force means atoms are locked in a lattice or lattice structure, which in turn makes them hard and brittle because they're locked in so tightly. Another thing about lattice structures is that it has a high melting point and boiling point and a low conduction point because the atoms are so locked, so tightly packed together that there's no space to for electricity flow. So in order to have good conduction, you have to have freely flowing particles, which since they're locked in, they don't have. Okay, so now we're going to talk about Unit 2.4, structure of metallic metals and alloys. So metallic bonding consists of good conductors of heat and electricity. As we know before and talked about before, there's a sea of electrons that we see, but alloys is a little bit different. Alloys are homogeneous mixtures. So, like we see in our coffee is a homogeneous mixture, while cereal is not, because in cereal we can see every different part, which means it's heterogeneous. But in coffee we can see that it's homogeneous. Alloys also have the characteristics of metals, but there's two types of alloys, one being substitutional alloys and interstitial alloys. And we'll get into that a little bit more. But basically, substitutional alloys are bigger atoms and interstitial are smaller atoms. Yeah, so let's talk about substitutional versus interstitial. So substitutional, as by the name, we see metal atoms are subbed or substituted for other metal atoms. And an important thing to memorize is that they're similar in size. So they're going to show you graphs, but they're similar in size. And they also have metallic properties. However, for interstitial, metals are not replaced. Our metals are filled with other atoms, likely carbon or a certain gas. And they're not similar in size. That's very important to memorize. And they also have different properties. So let's draw a line and show a couple examples. So you're going to see these kind of examples on your AP exam, and really it's important to know which is substitutional and interstitial. So the red represents one atom and the black represents another atom. And basically they're similar size, and it just shows that the black is substituted into the red. However, in the interstitial, we see the whole structure is big metal atoms, and then in between there's blue atoms, and those are often carbon, and they're filled in between, but you can see that they're different in size, and they're just filling the gaps. So in this example, it's iron and carbon in between, and iron and carbon make steel. And now we're going to talk about Unit 2.5, Lewis diagrams. So Lewis structures, as you've probably known about in regular Chem or Chem honors, they're just a bunch of dots, lines, and chemical abbreviations. And they're going to reflect the octet rule, which means, if you don't remember, that every atom wants 8 electrons. So it needs 8 to be stable. However, there are some exceptions, as we're going to talk about below. Hydrogen, for one, only needs 2 electrons. Beryllium only needs 2 electrons, or can hold 4 electrons. And boron only needs 3 electrons, but can hold 4 electrons. But then we can also talk about the expanded octet, which we'll expand on in a little bit. So for row 3 and below on the periodic table, they can actually hold more than 8 in their empty shells. So we'll talk about that a little more. Let's do an example. So we have Pi3. P, as we know, has 5 electrons and I has 7. However, there's 3 of them. So we have to multiply that 7 by 3. So we get 5 plus 21, which we get 26. However, what I like to do is divide it by 2 so we get the amount of pairs. So now that we have 13 pairs, we're going to write out P is going to be in the middle because it's the least electronegative, or because there's 3 I's and only 1 P. So we're going to put 3 pairs, so that means there's 10 pairs left, as you can see by the 3 lines. And we're going to put 3 sets of 2 dots on each of the I's, which is 9 pairs, which means we only have 1 pair left. So we're going to put that pair on top of the P, which means we have 0 pairs left, which checks out. And now we have to check. P has 8 electrons around it. All of the I's have 8. So that is a check for the octet rule, and that's what we want to make sure about. All right, let's do another question. So let's do NH4 positive. So when it's a positive, that means we're going to have to put them in brackets and then put the charge in the top right corner. So we know N has 5 electrons and H has 1, but since there's 4, we have to add them. So that's 9. But because there's a positive, we have to subtract 1 electron and giving us 8 electrons. So 8 divided by 2 is 4, so we have 4 pairs to work with. N is going to be in the middle because there's 4 H's, so we surround the N. And H only needs 2 electrons, so we've already passed this because we've used all 4 pairs, and H and the N's all satisfy the octet rule. And then, as we know, we have to put it in brackets, and we have to put the charge in the top right corner. Obviously, it's a little smushed, so I think we'll write it up here again. The whole thing is going to be in brackets with the charge in the top right corner. All right, let's do a more difficult question in reference to expanded octet. So we have ClF3. Cl has 7, F has 7, so our total is 28, and we have 14 pairs. So Cl is going to go in the middle, F's on the outside, and we're going to just give up all our pairs. So as we can see, all the F's fill the octet, but we have 2 pairs left. But we don't know where to put those 2 F's, those two pairs. But because Cl is in the 3rd row and below, it can have an expanded octet, which means Cl can have more than 8 electrons. So with these 2 pairs, we're going to put them just next to Cl. So now you can see that Cl has 1, 2, 3, 4, 5 pairs. And these are lone pairs, we call them, because they're not attached to anything. And as we talk about later, lone pairs will affect polarity. Anyways, let's go into type of bonds. This is pretty simple, honestly. We have pi bonds and sigma bonds. So if it's a single bond, it's just going to be a single sigma bond. If it's a double bond, it's going to be a sigma and a pi bond. And if it's a triple bond, it's going to be a sigma and 2 pi bonds. So an N2, or nitrogen gas, we see there's a triple bond here, which means there's going to be a 1 sigma bond and 2 pi bonds. Pretty simple. All right, moving on. So now we're on to Unit 2.6, resonance and formal charge. So when we talk about resonance structures, it might seem a little confusing at first, but once we break it down, it'll make more sense. So resonance structures are basically a group of 2 or more Lewis structures that collectively represent a single polyatomic species. So what does that even mean, right? If you're confused, then that's okay. So let's break it down. So let's continue about resonance structures. So what do they show? Resonance structures show unequal bonds. And when we write it, it's always going to be in brackets, but there's going to be different versions. So version 1, version 2, maybe version 3. And they're going to have these lines in between them. And obviously at the top, there might be a charge, and we're going to write that only if needed. But these lines symbolize that they can go back and forth, and they also symbolize that the real molecule is an average of the 3, or 2, or how many there are. So here's an example. So we're going to do a hybrid resonance structure of CO3 2-. So it's very similar to a regular resonance structure, but we're going to put all versions into one. So we're going to put C in the middle and L's on the outside, making sure to give our dots correctly, just like a regular Lewis structure. But you see, we're going to have to put one more pair, and we can put it with a C. But now it's unequal because one O doesn't have it, and another O doesn't have a double bond. So that means one version is going to have it on the left side, one's going to have it on the top, and then one's going to have it on the bottom, because we have to make it equal. So in this case, if we're doing hybrid, we're going to just draw dots to represent that all 3 are an average of the 3 versions that we didn't include. All right, let's do an example. So HCO2 -1, which means we have to put it in brackets and have a charge. H has 1 electron, C has 4, and O has 6, but we have to multiply by that 2. So we get a total of 18 electrons, and we have to divide that by 2 to get 9 pairs. So when we draw our structure, our first structure, we have to distribute our electrons properly. And because C only has 6, it does not fill the octet. So we're going to have to put one of the lines to fill the octet. But one of the O's is left out. So now we have to do our other resonance structure. So we're going to do the same exact thing, but the bottom O is going to have the 2 dots this time. And we're going to add the brackets and fill the charge. So this will be our answer. And as you can see, everything fills the octet rule, and H only needs 2, so we filled the octet rule. So what about bond order? A question might ask you, what's the bond order of one resonance structure or hybrid resonance structure? And it's very simple. So we're going to break that down now. So often we use the BO formula. So BO, we're going to look at the amount of unbonded electrons. So there's 2 groups. There's unbonded electrons on O and another O, so that's 2. And then there's 3 bonds that are connected to C, the middle ion. So 2 represents how many elements are connected to the center, and 3 represents how many bonds are connected to the center. So therefore, our bond order is 1.5. All right, let's talk about formal charge. Formal charge has a formula. It's pretty simple. It's the number of valence electrons subtracted by the lone pairs subtracted by half the bonded electrons. And I recommend you memorize this, and now we'll go into a little example. So for O, we know that O has 6 valence electrons, and we have to subtract the amount of lone pairs, which is 6. And there's 6 minus 6 equals 0, and then there's 2 bonded electrons, but it's only half, so therefore our charge is -1. For C, there's 4 valence electrons, 0 lone pairs, and 4 bonded electrons after dividing. So that gives a charge of 0. O is 6 minus 2 lone pairs equals 4 minus 3 bonded electrons, which gives us a +1 charge. So those are our formal charges. It's pretty simple if you follow along with the rule. So using formal charge in our resonance structures, we have to determine what is the best Lewis structure. Using our formal charge knowledge, we have to determine which of the structures is the most efficient. As you can see in the first one, there's a triple bond, there's double bonds in the second one, and there's another triple bond in the third one. So here are some things we're going to need to look at. What we're going to be looking for in the best Lewis structure is the minimum number of non-zero formal charges. And if it is non-zero, we want that charge to be negative. And if it's negatively assigned, we want that negative charge to be assigned to the most electronegative atom. So these things will help us determine which is the best Lewis structure. So we're going to find the formal charges of every single atom here. So we know that N has 5 valence electrons minus 2 lone pairs subtracted by the amount of bonded pairs, which gives us 0 for both N and C. And then we see S has a -1 charge. We see the total charges of N, C, and S equal the charge in the top right corner of the brackets. So we're going to do the same thing, finding the formal charges for each atom. So N has a -1 charge, C has a 0 charge, and S has a 0 charge. So let's calculate the last couple. So N has a -2 charge, C has a 0 charge, and S has a positive 1 charge. So now we're going to look at first the minimum number of non-zero formal charges. In the first one, there's only 1. In the second one, there's only 1. But in the third, there's 2 non-zero formal charges. So therefore, the third one's not going to be our answer. And if it is non-zero, we're going to look for negative. So the first one has a negative non-zero, and the second one also has a negative non-zero. And the third does not, so it also proves why it's not the right answer. But now what do we do? Because there's 2 that are fitting both the recommendations. The negative charge is assigned to the most electronegative. So we're going to look at this. This will determine whether 1 is the best Lewis structure or not. So our answer is going to be the second one, because S is not as electronegative as N. So therefore, this is our most dominant Lewis structure, because N is more electronegative than S. Okay, let's talk about Unit 2.7, Vicepar and bond hybridization, or you can call it Vispar. So Vispar or Vicepar stands for but before we get into that, let's talk about Lewis structures. So Lewis structures don't talk about geometry, right? This diagram right here does not show 3D. You know, those 2 might be in front, some are going to be in the back. So valence shell electron pair repulsion is what Vicepar stands for. And basically, negatives repel each other, and bonds and lone pairs are negative because they're made up of electrons. So let's continue with that thought. So Vicepar focuses on electric domains, and we're going to be looking at bonds and lone pairs as things. So in this diagram, we have 3 O's and 1 C. So we're going to look at the lone pairs and bonds, but we're going to look at things. So there's 3 things here that connected to the center. So we call that 3 things, or 3 electron domains. But let's say there was 2 dots in the middle. That would be a lone pair, which makes it 4 things. So we're just going to count the number of things that are connected to the center. So here's an example. So we're just going to do some random letters to symbolize atoms. And there's a single lone pair on top, and then there's 2 atoms connected to the center. So there's 3 things, which makes 3 domains. And if you look at your Vispar geometry chart, you're going to see a category for 3 electron domains, and it's going to tell us our bond degree. As you can see, this is a less than 120 degree, and it's going to symbolize a bent or angular shape. As you can see, it's kind of bent. It's not a straight line. So you're going to have to memorize almost all of those. But what you're going to have to memorize is 3 things. You're going to memorize the degree, which in this case is less than 120 degrees, the shape, bent or angular, and the domain numbers that are connected to it. All right. Now let's talk about polarity. So in our Lewis structures, if the structure is symmetrical, it's going to be nonpolar, and if it's asymmetrical, it's going to be polar. So as you can see, NH4 is symmetrical, and therefore it's nonpolar covalent. So let's get into a polar asymmetric example. So CO2, as you can see here, let's get into a nonpolar symmetric example. This is nonpolar. As you can see, it's symmetric on both sides, and the charges, those lines are pointing to the most electronegative, which are the O's, and those lines are equal in size. So therefore, we can just cancel them out, like math. So if there's no lines, no electronegative lines, it's nonpolar. Now let's get into a polar example. So here's an example, H2O. So there's 1 O and 2 H's, right? The O is going to have 2 lone pairs. So if we put the lines to reference the electronegativity, it's going to point to the H because obviously it's more electronegative. So there's 2 up there. But then there's also 1 at the bottom pointing up. So the charge itself is we're all looking up towards the electronegative atom. But in this case, even if we were to cancel out those charges, there's still one line there, so therefore it's polar. All right, let's get into hybridization. That's a hard one to say. So we know carbon has a order of 1s2, 2s2, and 2p2. As we can see, the 1s shell has two, one going up and one going down. Those lines represent the spin. And then the 2p2 has three different groups, but since we only have two in there, as shown by the exponent, we're going to put two in there. But we can't put them together. We have to put them separately first. Until we fill all three, then we can put them downwards. So what does this show? This shows that carbon has two unpaired electrons. And it can only form two bonds. But it can hold four. And the reason why carbon can hold four bonds is because of hybridization. So let's talk about hybrid orbitals to understand this concept. So carbon, when it's unbonded, it's going to be 1s2, 2s2, and 2p2, with the 2p lines going straight up. However, when it's bonded, we're using hybrid orbitals. So therefore, the 1s2 is the same, but this time, instead of the 2p and the 2s, it's going to be sp3. And there's going to be four lines going up, which represents four hybrid orbitals. And this is so we can fill more space and have more bonds. So, thank you. This is the end of chapter 2. I hope this helped. Some other resources that you can that can help you practice and that helped me to get a good grade on the test was Khan Academy. They're really good. I got some of this work from Khan Academy. Fiveable is a great one to practice and have some reading available to you. Organic Chem Tutor on YouTube and just other YouTube videos in general. And then Quizlets. The teacher might give you a Quizlet or you can make your own. And then AP Classroom, those AP Daily Notes and the practice. So thank you for watching. Goodbye.